G'day, it's Richard Marra here again at Mars Classes, and we're looking this time in this episode at the forces that moving charges and current carrying conductors will experience when they're placed in magnetic fields. Now, we've already stated previously that a moving charge, as it moves, its electric field lines will be distorted and create a magnetic field around that moving charge. We've also said that we can display the direction of the field by putting a cross to indicate the field is going into the screen or into the page, and a dot is indicating that it's coming out of the screen or out of the page. So that has a magnetic field, and we know that magnetic fields will influence other magnetic fields. We know that like poles attract, like poles repel, and unlike poles attract. So if we have a moving charge entering a magnetic field, the magnetic field of that moving charge will interact with the permanent magnetic field that's already there, and that charge will experience a force. So in this example here, we've got a positive charge moving up into a field which is coming out of the page. When it enters the field, you'll see that on the left-hand side, where its field is in the same direction as the permanent field, it's going to strengthen the field in that side of the charge, and on the other side where its field is going the opposite direction to the permanent field, the magnetic field will be weakened. Now when that happens, you're going to get a force in the direction indicated there, and that force, you'll notice, is also perpendicular to its velocity. Now we've looked previously, when a force is perpendicular to a velocity, you end up with a centripetal force, and the thing will travel in a circular path. Now what's occurred there is what would happen in the mass spectrometers, which I mentioned previously in an earlier episode. So what things are going to influence the size of the force that this charge experiences? Now it's in a magnetic field with a magnetic field strength B, it has a velocity V, and it has a charge Q. So those three values there can be combined to give the overall force. The force equals BQV, and that force is equivalent to the centripetal force. So we'll have BQV equals mv squared on r, and you can rearrange that to see that the mass to charge ratio is equivalent to BR on V, and that's the type of work we do when we look at a mass spectrometer. We look at the radius of the path taken by the charged particle as it enters the field, and that gives us an idea of the mass and or charge of that particle. Okay, let's have a look at a straight current carrying conductor, because remember, a current carrying conductor is just a wire that has a number of charges moving. Now if each one of those charges has its own magnetic field as it moves, in this case we've got the current travelling up the conductor, and there's going to be a lot of charges moving up the conductor, each one will have its own magnetic field. So around that conductor you're going to have quite a strong magnetic field. Now using our conventions, if we look at the top of the conductor, we'll see that you can indicate the direction of the field, the direction of the current by a dot coming out of the screen, and the direction of the field by those blue arrows. Now how can we work out what direction the field is going with ease? What we do is we use a right-hand rule, which is called the right-hand grip rule. And with this rule we say if we use our right hand, only our right hand, and the thumb is in the direction of conventional current, remember that's the direction a positive charge would be flowing, that's the direction that goes from higher electrical potential to lower electrical potential. If we use our right hand in that grip sort of shape there, and the thumb is in the direction of the current, our fingers will curl in the direction of the magnetic field lines. So we've got this demonstrated here on this screen for a current going up the page. We can do the same thing for a current going down the page. Now let's see what would happen if we then place that current carrying conductor into a magnetic field. We saw that an individual charge would be experiencing a force always perpendicular to its motion. With a current carrying conductor, the charges are constrained within the conductor, so even though they'll be experiencing a force that wants to be perpendicular to its motion, it's not going to make it travel in a circular path. In fact, what you'll get is when you place the current carrying conductor into a magnetic field such as the one I've got here, you'll notice that at the top the field will be weakened because the force, the field of the conductor is in the opposite direction to the permanent magnetic field, but below the conductor the field that it produces is in the same direction as the permanent field. So you'll experience an upward force, and that can be drawn in a diagram similar to the one at the bottom. Now, if we had a conductor coming out of with the current coming out of the screen in the same magnetic field, we'll see that the field would be strengthened above it and weakened below it. And to illustrate what occurs there, we have a little animation here which shows what occurs. So you get this sort of pressure above of the density of the field lines pushing the conductor out of the field. Now, sometimes you won't have a permanent magnetic field. You'll have a current carrying conductor with its own magnetic field around it. Now, again, remember, we determine the direction of that magnetic field by using our right hand. Our thumb is in the direction of the current, and on the left-hand side, the dots represent that the field is coming out of the page or the screen, and on the right-hand side, the crosses indicate that the field is going into the screen. Now, if we placed another conductor that is carrying a current near that, and therefore it would be in the field of this first current carrying conductor, and I've got the instance here where this is carrying a current in the opposite direction, and again, if we use our right hand to determine the direction of the magnetic field on this second conductor, we'll see that when you do that, that the area between the two conductors, both magnetic fields will be adding together to strengthen that magnetic field between the conductors. So what you'll end up doing is that pressure or tension in there where the field has been strengthened will push the two conductors apart. And again, that can be represented in a diagram like this. You could also have it such that this current carrying conductor, you placed another current carrying conductor near it which was carrying the current in the same direction. And when you do that and you look at the field between the two conductors, you see now they're going to be in opposite directions, so the field will be weakened. And when that field's weakened in there, you'll find that there's a pressure pushing the two conductors together. Okay, now when we're looking at the factors that influence the size of the field, we know that that it was the magnetic field strength, we know it was the velocity, and we know it was the charge. So we know that we can say that F equals BQV when we're looking at just one charge moving through a magnetic field. That's the force it will experience. But if we're trying to work out what force a current carrying conductor will experience, we'll have to utilise another equation. Now we know that velocity is actually just distance or length per unit time, so we can rewrite that F equals BQV as F equals BQ L on T. Length on time is equivalent to velocity. And if we rearrange that, we could write it as F equals LB Q on T. And we also know that Q on T is current, because current is the rate at which charge moves. So we could write that as LBI, or more usually written as ILB. So fantastic. We've now worked out how we can determine the force that a current carrying conductor will experience when it's in a magnetic field. This is going to become invaluable when we're looking at electric motors, because that's what causes electric motor to turn. The wires in the coil of the motor are experiencing a force which makes it turn. Okay, so we know how to work out the magnitude. How do we work out the direction? So the magnitude is worked out by F equals ILB. To determine the direction, we use another right-hand rule, and we call this one the right-hand slap rule. And with the right-hand slap rule, again, our thumb is in the direction of the conventional current. And again, our fingers are in the direction of the magnetic field. Although this instance, we have our fingers out straight because we've got the current going perpendicularly to the field. And our palm is pushing in the direction that the force will be experienced. So we can use that right-hand rule to work out the direction of the field. And remember that when it's maximum force, the current, the field, and the force are all mutually perpendicular. So we can use the right-hand rule to determine the direction of the force. But to explain the direction of the force, we've got to look at the fact that the magnetic field of the current carrying conductor is interacting with the permanent magnetic field, and that's where the force comes from. So if you're ever asked to explain the force, you have to talk about interactions of magnetic fields. You can use your right-hand palm rule just to predict the direction, but it's only a predictive tool, it's not an explaining tool. Okay, I think that's enough for this instance. What I'll do is I'll leave it there, and we're going to come back and we're going to look at how we can utilise this in electric motors in a future episode.